Good afternoon, everybody. My name is Kevin, and welcome back to the ESP32 Product Creation Journey. I was out all last week. I had to, on short notice, do some travel to handle a family situation, but we are back and ready to go. And what I want to do today, in today's episode, is we got new hardware. Check it out. Here's the blue version of the boards that we got from our redesign. We have those in. Took a little while to get in, component shortage and all going on. But as a brief, I'm not going to call it a pro tip, but a tip of sorts. Here's the last version. You can see that it is red. And it's not that I like blue. Blue is my favorite color. But not that I like blue better than red for boards. It's just in the early stages of going through these different batches, I like to choose a different color. That way it's very easy for me to tell what's new hardware versus old hardware, especially if there's only minor changes that are hard to notice just by looking at the board. If I've got a red one and a blue one sitting right next to each other, it's really easy to know that my latest hardware is the blue. I haven't decided what color we're going to do with the final version that's going to go in the product, but so anyway, we have boards in. We have 5 of them, and we ran into a problem right out of the gate, and I want to talk about that and talk about how I panicked, and then I think we've got it figured out. So, excuse me. I coached my daughter's soccer game again today, so my voice is a little tired. All right, I want to show you some behavior that we get here. Let's get a shell out here. Source. IDF. I don't know how long this stream's going to last, just as a heads up. My family might need me for something. I normally try to schedule in streaming, but we're just going to go with it. So if I have to cut off abruptly, I apologize. Export.sh. Okay. Great. Okay, now we're going to take the old hardware, the red board here, and we're going to plug it in. And what we're going to do is we're going to flash it. We're going to do, and I'm going to flash it from the command line, and you'll see why, just so I can do it faster over and over here. We're going to do flash, okay? It's going to go through. It shouldn't need to build. And linking. It's going to go through it. And what you'll see is 100% built target flash. Wrote that many bytes of data, and it says hash of data verified. Really cool. All right, let's do it again. We're going to do it 5 times. And this is time number 2. And you can see it succeeded. Let's do number 3. And it succeeded. Let's do number 4. It succeeded. And number 5. And it succeeded. 5 for 5. And that's what we want to see. We want to be able to program this thing. No issues, no hiccups, rock solid. Old hardware, 5 for 5. Programming, no problems whatsoever. And you watch, this isn't going to work because I'm filming, but we're going to do it anyway. I'm going to plug in now the new hardware. I actually marked these just in case there's issues. I can track them. This is board number 1. And what we're going to do, we're going to plug board number 1 in, and we're going to hit flash, see what happens. And it looks like it's programming. It goes through its own thing there, and oh, darn it. What happened? A fatal error occurred. MD5 of file does not match data in flash. And it'll show you, here's the file MD5 from our firmware, and here's the flash MD5. They do not match, which I actually really appreciate that the tooling here checks for that during a flash. So it's saying here's the checksum of the bits that we were supposed to that are part of the firmware, and here is the checksum of the bits that are actually on the flash, and they do not match, which means something went wrong during programming. All right, let's try number 2, see what happens. Come on, no whammies, no whammies, and it failed again. And you get this, flash error. Same thing, fatal error MD5 does not match. What the heck? Let's try it again. So I don't think I need to do this 5 times for you to realize that something, oh, look at that. This couldn't have worked out better. Wrote data, hash of data verified, we're all set. Okay, so out of 3 flashes, it's worked 1 time. Okay, and we'll try it one more time just for kicks. I don't think we need to do 5 to prove my point here. Let's see what it does. Oh, it failed again. Okay, so 3 out of 4 so far failed. Just for kicks, let's do 5. While that's going, this freaked me out. So when I first got the hardware, I took it out of the packaging. Look at that, succeeded. Okay, so out of 5 program flash attempts, 2 succeeded, 3 failed. And what happened was I got the hardware. I wanted to just do a sanity check. Like, does it work? Does it program? There's no buttons on it. Like this old hardware here, you can see it's got the buttons here and here, the header on there and all that other stuff. The new hardware is like more production. There are no physical buttons. Fiddle. Like, it's not gonna... Sorry for the crappy camera. There's no buttons on it. There's no header on it. And so there's no way for me to manually reset it with a button or put it into boot mode based on the ESP-IDF logic of like holding down boot while hitting reset. I can't do that. I'm relying on the FTDI and the RTS and DTS line signals and everything in our design to reset this and put it into the right mode so it can be flashed. And it's only working 2 out of 5 times. That's not a great... Let's see. Let's do the math. It's only working 40% of the time, failing 60% of the time. I probably did the math wrong on that. Anyway, the first few times it programmed just fine, and I was like, oh man, great, it's working. And then I started getting these, like where it would fail. And so I was like, oh, I've never seen that before. Let me try it again. And for a while, like the second time I would try it, it would succeed. You can see it's really hit or miss. And so I was like, oh, that's interesting. But then the other night, I realized... I'm going to unplug this. It was failing a lot. I'm talking like 7, 8 out of 10 times it would not program, which started to really make me worried of like, oh my goodness, what has our hardware change done here? And so I got really worried. For those that have been following for a while, let's just open it up here. Let's go into the main view here. Let's unfill these. You'll probably remember, let's just look at this really quick, that here are the data lines from the USB. They come through, and they've got some TVS diodes and some, I believe, capacitors. 16 and 15 there. And then it goes through 2 resistors into the FTDI chip. And you remember, you want to keep these runs as short as possible, as similarly lengthed. That's not even right. You want the length to be the same so that there's less chance of data distortion, because again, USB works on a data differential, not a 1 and 0 type concept. And so you don't want anything interfering with it. And you can see I ran 2 new lines underneath here, power enable and the BCD. Is it BCD? Yeah, BCD. Battery charge detect and power enable from the FTDI chip to the PMIC. And when I did the layout, I said these shouldn't cause any sort of data problems at all because of the USB lines. But immediately I started to worry that maybe putting those lines under there had somehow started disrupting the data, or maybe at first I thought maybe some of the components, the hardware's bad, so I grabbed a second board and I tried it. I was getting the same issue. So that's just basic troubleshooting, like try another board, make sure it's not the hardware. Multiple boards were doing the exact same thing, so I knew it was unlikely that all of the hardware was bad, because the hardware is normally pretty good that I get through PCBWay. And so I started panicking of like, oh man, something is causing this. And then I remembered something, and this is important. What I remembered is, in fact, it's these 2 lines. If you recall, we have made a design change so that the device is actually USB compliant, meaning it will not pull more current from the port than allowed by USB spec. Manus, thanks for joining. Great to have you. So that was a conscious decision that we made. We changed the design so that before it would try and pull as much current as it needed from the USB port, and I wanted to make it so it was compliant with USB spec, which I realized I thought the boards would enforce, but they do not. Like the motherboard in your laptop or on your tower is not going to enforce that most likely. That was something that we learned. And so I wanted the device to be USB compliant, which means it cannot draw more than 100 milliamps of current without requesting it, and this is USB spec stuff. And when the device is in sleep mode, it can't draw over, I can't remember what it is. It's low milliamp or even microamp maybe. But anyway, I found out that the device doesn't actually enforce those limits. It'll give you whatever you ask for up to what the hardware can provide, which is what a lot of devices do. And in fact, what is happening with, well, sorry, wrong hardware, the red hardware here. So what is happening, I believe, and the way I will show you that I think I'm right on this, is that because of how we have this configured, you remember, we did this whole spreadsheet to determine, whoa, where are we going here? To determine which lines to connect out of the FTDI down to the PMIC to control the max USB output from the PMIC, max current draw. And without programming the FTDI chip, those are probably not set right, and so it is probably limiting the amount of current that it will allow to pull from the USB port. And so what I actually believe is happening, and we're going to hopefully prove this in this stream, is that because I haven't programmed the FTDI chips, they come a certain way from the factory, we'll look at that in a second, it is limiting the amount of current, and it's probably browning out. Now, the way to get around that is a battery. If a battery is connected, the PMIC will draw whatever it needs. It's going to first try to favor the USB power source, but if the USB power source isn't enough, the PMIC on here is smart enough to say, I'm going to take whatever I need from the battery. And so it has that ability to seamlessly switch between the two power sources. And so all we're going to do is I'm going to plug in a battery here, which gives us an infinite supply, not infinite, but gives us way more power than we need for programming. And now I'm going to plug it into USB. And now, we can get rid of this for now. And this. Now let's come back, and now let's try to flash it a few times. Okay? So now it shouldn't brown out because the battery's on there. And you'll see it worked just fine. Let's do this a few times. Here's time number 2. Built a target flash, hash of data verified. Let's do number 3. And these are good things to do in general, like programming it over and over and over again, just to make sure that the quality and the hardware is deterministic, like it's going to perform the same every time and there's not some weird things going on. This is time number 4, I believe. Well, I don't know what I was doing there. 4. And it worked just fine. And let's do 5, and we should be a solid 5 for 5, confirming our theory. Perfect, great. So see that just by adding the battery, I'm gonna go ahead and unplug that now. Just by adding the battery, it programs fine every time now, which again supports our theory that because the FTDI chip is not programmed on here, the PMIC is not allowing enough current to come from the USB port, which means it's probably browning out during flash, and then the hashes aren't matching. So I had forgotten that we had to do this. So this is an important thing to remember. We need to program the FTDI chip on every device. So as part of the process for delivering this, we're going to have a script that programs the FTDI chip and then programs the ESP32 as well. And again, the reason for that is that our device should be 100% USB power spec compliant based on how we have designed it. So to look at this, we're going to open another window. Okay, And we'll CD into sorry, I don't know why I pulled that away from you here. Okay, right there, front and center. I did a stream on this a while back. I'm not going to rehash this. This FTX Prog is a Linux utility. There's a Windows and a Mac version of this that will program FTDI chips. On Linux, there's a command line version that allows us to, I just built it locally. If we look at the directory here, it's just a single C file. And then it builds this FTX Prog that we can run, FTX Prog, and it'll show you what all of the options are. And so what we're going to do is dump. So we're going to plug in, and then it should detect and find it and do everything. We have to run it as sudo. That's an important thing because it needs access to the hardware. Dump. Okay. Now let's take a look at some things here. There's a couple of things that we're going to need to program. First of all, battery charge detect enabled is false. We're going to want to enable that, I believe. Where is... Oh, I already fixed this one. Okay, by default, the FTDI maximum current supported from USB is 90 milliamps. Now, that's not as simple as it sounds. It's not going to limit our PMIC to drawing 90 milliamps. It's going to limit the FTDI from drawing more than that. Well, sorry, I'm lying there. This is to help, I believe, in the negotiation process to request the amount of power that it can draw. And in that episode where I go over FTX Prog, you can actually do some USB command line. Is it LSUSB? There's a command line argument that you can interrogate the hardware and it'll show you like, hey, from a system perspective, I've granted it this much power. So it's set to 100. It comes as 90. And so I want these set to 100 because that's the max that they'll draw. And then if we come down here, CBUS. The default behavior of the CBUS 0 line is transmit enable. I'm not sure what that is. Transmit data enable. Yeah, TX data enable. CBUS 1 is the receive LED. So like if you were to hook up, you could hook up LEDs to the CBUS lines on the FTDI chip, and it'll give you that, like when it's communicating, it'll give you that flash. Kind of, they flash to show you like, hey, data is being sent or received. And so that is the default. Hold on a second. I got to yell at a kid. Stand by. Yep. Okay. We're back. Sorry. Kids, I'll tell you, you gotta stay right on top of them. Okay. So we don't want the CBUS lines to be these things because if you remember, let's go back into it. I don't want to rehash all the schematic stuff, but this one is just, it'll be good to go over. You can see that in here, our CBUS 0 line. Oh my goodness, these kids. To the backyard. You may not be out here. No, you're in the front yard. I love all of them to death. I do. Okay. The CBUS 0 line is our battery charge detect, and our CBUS 1 line is power enable. Now, by default, as I just showed with the terminal, that's not how they're configured. So we're relying, and then they go out to BCDN power enable. Let's check and see where that goes. Backspace. We come up here. Those come in to where? Right here. To the enable 2 and the CE line. And again, we did a whole episode on why we did it this way, but Anyway, those lines are controlling how the PMIC performs. And so in their current state, the PMIC's not doing what we would like it to do. And so we need to fix that. We need to enable battery charge detect. And we're going to have to look at the data sheet on that. Let's do that. Oops. That's the FTDI 231. Okay. Let's grab this over. And this is our, I need a data sheet. There we go. Documentation, data sheet. Battery charge detect indicates when the device is connected to a dedicated battery charger. Active high output. Inverse of BCD. This is how we want to set it. We want to set it as inverse of BCD charge, because if you can see here, we have the line above it. And I talked about this before. The line means the inverse, so it's expecting the inverse. And then we also need to see about whether we need to enable. I think there's a whole section on it. Let's go through it here to make sure we're doing the right thing. Package print memory map, methods of internal, here we go. Internal memory configuration. And you can see here the CBUS lines. Look at this. Default configuration of CBUS 0. Transmit data enable for RS485. So that's what that, again, TXDEN equals. And you can see CBUS 1 is RxLED, which is right here. TXLED and sleep. So exactly what FTX Prog is telling us. And CBUS 3, 4, 5, and 6 are tri-stated, which we don't have here in this in the data sheet. So what we need to see is there was something in the data. Yeah, and you can see here, this is what I mentioned earlier. 90 milliamps is the default for max bus current. Okay. So I'm curious why. I wonder if the output here, because remember right here, see where it says up here, battery charge detect enabled is false. I wonder why. So let's run this again. I'm wondering if we just enable one of the CBUS lines to be BCD, if it will work. And so, yeah, because I don't see anything here that like changes that. Okay. So what we're going to do is, you can see right here, we can pass CBUS, give it a number. It says 1 to 7, but I don't know if that's true or not. And then here are the options we can give it. We can give it tri-state, RxLED. What we're going to want to do is give it BCD charger. Another way to say the inverse is this pound symbol. And so we're going to name which. CBUS 0 is going to be BCD, and CBUS 1 is going to be power enable. Okay, so let's try. Let's try and set CBUS 0. Let's see how we do this. And we'll say BCD charger pound. BCD underscore charger pound. Let's see what that does. Oh, look at that. It did. That is, so the help message is wrong. It's not 1 through 7. It would be 0 through 6. Okay, so that's yes what we want to do. So I'm going to say no. And because I'm going to do them both at the same time, I'm going to say CBUS 1 power enable, which I believe is the option. Again, even though it is inverse, you don't have to specify it as inverse. So let's do that. Now see what we get. Because again, it'll do it'll show you, hey, this is what I'm going to write to EEPROM. And now let's scroll up and see what it says up here for battery charge. It still says battery charge detect enabled equals false. So seems like we may need to do something else there. Okay, but for now, I'm going to say yes, because that is what I want. And now, if I just do dump, you can see that those are programmed how we would expect. Okay, and it still said battery charge detect enabled equals false. So there must be some command we can do to enable that. Let's just take a look through this really quick. New PID, new vid, old PID, old vid. FT1, no. Max bus power, product, manufacturer, CBUS 8-bit strings, restore, save, verbose, help. Okay, I don't see any settings for us to change that. So for now, and as part of the testing for all of this, we're going to have to determine what we'll do. I'm going to unplug this now, since board 1 should have its FTDI chip programmed. What we'll do eventually is we need to make sure like the charge current is correct to the battery. Like we have to do a whole bunch of testing, which I'm going to talk about here in a minute. We're going to wrap up here pretty soon. But I think we've got this thing programmed to where it should be able to pull 100 milliamp from the USB port. So let's test that first. And the way we're going to test that is just simply, we're going to try and reprogram it a bunch of times and see if it has the same issue without a battery. There's no battery connected right now. I'm going to plug this in, and I'm going to do flash. Now, again, this might not work because we don't have the battery charge detect enabled, but that shouldn't have anything to do with this. It should allow us to pull enough current. So let's see if it does. And it's also possible, okay, so that worked. Let's try it again. It's also possible that there's spikes above 100 that are causing it to brown out. That could also be possible. It might just need more than 100 milliamp to program. That's 2 for 2. All right, can we do 3 for 3? Big money, no whammies. 3 for 3, beautiful. All right, I think we may have resolved our issue. I said it too soon. I said it too soon, didn't I? 4 for 4? Come on. Yes. All right, let's see if we can do 5 for 5. And can they do the sweep? Beautiful. All right, that's great. Okay, board number 1's FTDI chip is programmed. It should be ready to go and charge the battery correctly. This is board number 2. It has not been programmed. The FTDI chip has not been programmed. So let's flash it, see what happens. Remember we did, I think it was 2 for 5 before. Look at that, it's not even detecting it. That's looking on the wrong port. That's a different error. Let's plug this back in. It's looking at the wrong port. I'm not sure why it's looking at TTY S4. Dev. It's not detecting board number 2 like at all. I wonder why that is. Well, that's no good. Let's plug board number 1 back in. There it is. So it's not detecting. Okay, again, this could literally be because the PMIC is in that like 2 microamp or 20, I think it's 20 microamp mode where like the chip like isn't even booting up. That's very possible. Okay, now it's finding board number 2. Okay, so let's try to flash it. Again, this is going to be, you're going to get all kinds of crazy behavior because again, we're controlling the PMIC with CBUS pins that are not properly configured. And you can see that our programming failed. We're back to having the same problem. So exactly as we would expect. And so dodged a bullet on that. I was really worried about a hardware change causing the issue, but just I had forgotten that we had specifically changed the device to operate differently. So now watch this. I'm going to just up here and I'm going to, so as part of the programming, I know it's kind of little, but this is the program, this is the command that we need to run. We just ftx prog CBUS 0 and 1, and I'm going to run that. Oh, because I'm not in the right. That's why. Let's come back over here. Let's run this. Right EEPROM, yes. Okay. And now I'm going to unplug it, plug it back in. I'll do the dump. And you can see it's properly configured now. We can exit out of this. And now our flashing should work just fine on board number 2. No, it's looking at the wrong serial port again. I wonder if that's because I'm switching them too fast, like, and not giving the system enough time. I'm gonna leave that. Let's give it just a second. Plug that in. Okay, there it is. And flash. We should be good to go. Okay, flash worked just fine. So great. That I'm going to call that problem solved. That worry that I had was just me not remembering the design that we made. Now, what we have to do next, which we're not going to cover today, is we need to make sure that those power enable and BCD lines are creating the correct behavior on the PMIC, meaning we need to see how much current is flowing in and out of the battery in certain scenarios with the, a laptop that's running or one that's in sleep mode. We need to make sure that we're following, again, the USB spec. There's a bunch of things that we need to test around that. I may or may not stream that. I want to talk about streaming in a minute, but I did buy a new toy that I'm really excited about. So in the past, I've tested the current out of the battery, like the charge current and the current that the device is pulling from the battery with a microcurrent from EEV blog. If you've ever watched that, Dave Jones down in Australia, which has been really great. I hook it up to an oscilloscope. I'll probably show that in a future, that's probably making a lot of noise, in a future stream, but somebody tipped me off to a new and improved version of the microcurrent. The microcurrent is an open source. Dave Jones open sourced it. He's not really making them and stocking them. And so I was lucky I got one a couple years ago, but some other member of the community has decided to take the reins and has created the Current Ranger. There you go. That focused pretty nice. There it is. And right now it's disassembled. It comes with some terminals to hook in there. I got the version that has a little OLED display. It auto ranges, and so on the old microcurrent, you had to switch between microamp, milliamp, microamp, and nanoamp. This one should auto range, and so I should be able to see the full spectrum of power usage when I plug this into my oscilloscope. It comes with a 3D printed case. You can either print that yourself or you pay a few extra bucks for him to print it for you. In the interest of saving time, I just asked for him to print it, and it turned out quite nice. And so I will assemble this, and we are going to use this to test the current draw and make sure all of those USB spec things are met, as well as get a very precise idea of how much current we're pulling from the battery when our application is running, so that we can give very accurate estimates on battery life, depending on the size of the battery. This is kind of stuff that it's awesome to know, so you really are zeroed in on the battery performance and things like that. And so we will take care of that in a future stream. And so That was great. Today we got the FTDI chip programmed on our 2 test boards here. We're going to continue to write firmware. At this point forward, we're going to use these new boards. I like to use the hardware as much as possible going forward as soon as I have it to, again, just get lots of repetitions on it, like lots of reps, to see if there's any problems that pop up or anything like that. And so a thought before I close and end the stream is I would like to get some thoughts. Streaming has slowed me down considerably. Like, I'm trying to provide a ton of value to the community of like the process of going through this while also not making the streams super boring. And maybe you think they're super boring anyway, but I'm trying my best not to make them boring and try to be packed with good content. And so I try to talk through everything that I'm doing. The problem is for those that have watched in the past, I am doing this to help other people, but I'm also doing this to launch a product for my business at the same time, which has a fast approaching deadline. I want to have all these things assembled and ready to ship by the start of the next hockey season, which is in October. We're already nearing the end of April. We are getting really short on time. And so streaming has really slowed that process down because I don't want to skip anything, but I also want to make sure that they're as compact and useful as possible. And so what I've thought about doing, and I would love feedback if you've made it this far into the video, thank you so much. But now I'm asking for some feedback and thoughts on an approach that I want to take, which is when I sit down, and I only have a limited amount of time. I have a full-time job, as many of you may know. And so I've got to pack in a lot of work in a short amount of time every single day in the evening. And I'm going to try and hack my schedule a little bit and get some of that in the morning. But I know a lot of people will stream, especially with like coding and things like that. They'll just turn the stream on and work and not really talk a lot, engage with the community here and there, but really just sort of like hit the record button and then just work through it. And I guess I could do that. The thing I hate about that is like, this is me going through the process. Like, I will spend an hour or two going down the wrong path. And then when I publish that and people are watching that, it's like, oh, let me watch them for an hour do the wrong thing. Like, oh, that didn't save me any time. And so I don't love that. But again, some people enjoy watching that. And so what I was thinking of doing is working and then shooting like an overview video, like a recap video of like, this is what I worked on tonight, and here are the things I learned, and let me show you and walk you through really quick, maybe a 20 or 30-minute recap at the end of my work sessions. So that's the thing I want to consider doing. I would love your thoughts on, as well as, would you want me to just stream the mundane, boring, I'm working? Because I'm happy to do that as well. I don't feel like I would upload those to YouTube because I feel like the end result on YouTube is people are looking to save time. If you want to watch the raw process, you can catch it on Twitch, and then making those little recap videos of like, here are some things I learned, some problems I ran into, and talk through some, knowledge share to help other people with their projects. And so that's the format I'm thinking. Work, then shoot a recap. I'm happy to stream the work part for those that want to follow it on Twitch. But anyway, I would love to hear your thoughts on how you might want to, what you think would work best, or what you would appreciate seeing as a member of the community. But that's going to do it for the stream today. I'm really excited that we didn't have, at least at this point, we don't have a major hardware issue that we need to resolve. It was just programming those FTDI chips. We're going to continue to write firmware. I want to, as soon as possible, get into a testing hardware and loop setup that I can then iterate on going forward. Again, the more reps of production ready that I can get, the better, so that I can have a very high level of confidence in the end product when we ship it in a few months. And so, yeah, we've got a lot to take care of. I should be getting cases in soon. Lots of cool things coming ahead. I appreciate everybody that's joined the journey, everybody that's reaching out on Discord and communicating with me and with each other. It's really been awesome to see. If you're not on the Discord server, I highly recommend you hop in there. There's a lot of great content happening there, and it's just getting started. I think it's going to grow tremendously with a lot of cool people showing up and helping one another and sharing projects. It's been really great. So thanks everybody for joining there. And again, thank you so much for watching. I hope everybody has a fantastic rest of their day and a good week or weekend, depending on when you watch this. And I will see you next time.